Hey guys, welcome back to another episode of my channel. My name is Keika. I'll be going over textbooks, chapter by chapter, section by section. This particular video will be going over Chapter 3, Water and Life, Chapter 3.2. And this is a concept within the chapter. 4 emergent properties of water contribute to Earth's suitability for life. Okay, so let's just get started. We will examine 4 emergent properties of water that contribute to Earth's suitability as an environment for life: cohesive behavior, ability to moderate temperature, expansion upon freezing, and versatility as a solvent. So, as you can see here, I wrote 4 emergent properties that contribute to Earth's suitability for life: cohesive behavior, ability to moderate temperature, expansion upon freezing, and versatility as a solvent. Cohesion of water molecules. Water molecules stay close to each other as a result of hydrogen bonding. Although the arrangement of molecules in a sample of liquid water is constantly changing, at any given moment, many of the molecules are linked by multiple hydrogen bonds. These linkages make water more structured than most other liquids. Collectively, the hydrogen bonds hold the substance together, a phenomenon called cohesion. One result of cohesion due to hydrogen bonding is high surface tension, a measure of how difficult it is to break or stretch a surface of liquid. At the air-water interface is an ordered arrangement of water molecules, hydrogen bonded to one another in the water below, but not to the air above. This asymmetry gives water an unusually high surface tension, making it behave as though it were coated with an invisible film. The spider in figure 3.3 takes advantage of the surface tension of water to walk across a pond without breaking the tension, and some plants can float on water as well. You can observe the surface tension of water by slightly overfilling a drinking glass. The water will stand above the rim. Cohesion also contributes to the transport of water and dissolved nutrients against gravity in plants. Water from the roots reaches the leaves through a network of water-conducting cells. As water evaporates from a leaf, hydrogen bonds cause water molecules leaving the veins to tug on molecules further down, and the upward pull is transmitted through the water-conducting cells all the way to the roots. Adhesion, the clinging of one substance to another, also plays a role. Adhesion of water by hydrogen bonds to the molecules of cell walls help counter the downward pull of gravity. So this is the water transport in plants. Okay. So for cohesion of water molecules, I wrote, cohesion is a phenomenon where hydrogen bonds hold a substance together, results in a high surface tension, which is a measure of how difficult it is to stretch or break the surface of a liquid. Water behaves as though it were coated with an invisible film. Cohesion contributes to the transport of water and dissolved nutrients against gravity in plants. Water from the roots reaches leaves via a network of water-conducting cells. Evaporation of water molecules from leaves causes an upward tugging. And adhesion, the clinging of one substance to another. Moderation of temperature by water. Water moderates air temperature by absorbing heat from the air that is warmer and releasing stored heat to air that is cooler. Water is effective as a heat bank because it can absorb and release a relatively large amount of heat with only a slight change in its own temperature. To understand this capability of water, let's first take a look at temperature and heat. Okay, so here I wrote, water moderates air temperature by absorbing heat from the air that is warmer and releasing stored heat to air that is cooler. And water can absorb and release a relatively large amount of heat with only a slight change in its own temperature. Anything that moves has kinetic energy, the energy of motion. Atoms and molecules have kinetic energy because they are always moving, although not necessarily in any particular direction. The faster a molecule moves, the greater its kinetic energy. The kinetic energy associated with the random movement of atoms or molecules is called thermal energy. Thermal energy is related to temperature, but they are not the same thing. Temperature represents the average kinetic energy of molecules in a body of matter, regardless of volume, whereas the thermal energy of a body of matter reflects the total kinetic energy, and thus depends on the matter's volume. When water is heated in a coffee maker, the average speed of molecules increases, and the thermometer records this as a rise in temperature of the liquid. The total amount of thermal energy also increases in this case. However, although the pot of coffee has a much higher temperature than, say, a water in the swimming pool, the swimming pool contains much more thermal energy because of its much greater volume. Whenever two objects of different temperature are brought together, thermal energy passes from the warmer to the cooler object until the two are the same temperature. Molecules in the cooler object speed up at the expense of the thermal energy of a warmer object. An ice cube cools a drink not by adding coldness to the drink, but by absorbing thermal energy from the liquid as the ice itself melts. Thermal energy in transfer of one body of matter to another is defined as heat. Thermal in transfer from one body of matter to another is defined as heat. One convenient unit of heat used in this book is the calorie. A calorie is the amount of heat that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Conversely, a calorie is also the amount of heat that 1 gram of water releases when it cools by 1 degree Celsius. A kilocalorie, 1,000 calories, is the quantity of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius. The calories on food packages are actually kilocalories. Another energy unit used in this book is the joule. 1 joule equals 0.239 calories, and 1 calorie equals 4.184 joules. Okay, so for my notes here, I wrote kinetic energy is the energy of motion. Anything that moves has kinetic energy. The faster the movement, the greater its kinetic energy. Thermal energy is the kinetic energy associated with random movements of atoms or molecules. Temperature represents the average kinetic energy of molecules in a body of matter, regardless of volume. Thermal energy of the body of matter reflects total kinetic energy, thus depends on the matter's volume. Whenever two objects of different temperatures are brought together, thermal energy passes from the warmer to the cooler object until the two are the same temperature. Heat is the thermal energy of transfer from one body of matter to another. Calorie is one conventional unit of data, which is the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius, also the reverse from cooling by 1 degree Celsius. Kilocalorie is the amount of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius, and calories on food packages are actually kilocalories. Joules is another unit of energy. 1 joule equals 0.239 calories, and 1 calorie equals 4.184 joules. Okay. The ability of water to stabilize temperature stems from its relatively high specific heat. The specific heat of a substance is defined as the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. We already know water's specific heat because we have defined a calorie as the amount of heat that causes 1 gram of water to change its temperature by 1 degree Celsius. Therefore, the specific heat of water is 1 calorie per gram and per degree Celsius, abbreviated as 1 cal over gram over per degree Celsius. Compared with most other substances, water has an unusually high specific heat. For example, ethyl alcohol, the type of alcohol in alcoholic beverages, has a specific heat of 0.6 calories per gram by degree. That is, only 0.6 calories is required to raise the temperature of 1 gram of ethyl alcohol by 1 degree Celsius. Because of the high specific heat of water relative to other materials, water will change its temperature less than other liquids than it absorbs or loses a given amount of heat. The reason you can burn your fingers by touching the side of an iron pot on the stove when the water is still lukewarm is that the specific heat of water is 10 times greater than that of iron. In other words, the same amount of heat will raise the temperature of 1 gram of iron the same amount of heat will raise the temperature of 1 gram of iron much faster than it will raise the temperature of 1 gram of water. Specific heat can be thought of as a measure of how well a substance resists changing its temperature when it absorbs or releases heat. Water resists changing its temperature. When it does change its temperature, it absorbs or loses a relatively large quantity of heat for each degree of change. We can trace water's high specific heat, like many of its other properties, to hydrogen bonding. Heat must be absorbed in order to break hydrogen bonds. By the same token, heat is released when hydrogen bonds form. A calorie of heat causes a relatively small change in temperature of water because much of the heat is used to disrupt hydrogen bonds before the water molecules can begin moving faster. And when the temperature of water drops slightly, many additional hydrogen bonds form, releasing a considerable amount of energy in the form of heat. What is the relevance of water's high specific heat to life on Earth? A large body of water can absorb and store a huge amount of heat from the sun in the daytime and during the summer, while warming up only a few degrees. At night and during winter, the gradual cooling water can warm the air. This capability of water serves to moderate air temperatures in coastal areas. The high specific heat of water also tends to stabilize ocean temperatures, creating a favorable environment for marine life. Thus, because of its high specific heat, the water that covers most of Earth keeps temperature fluctuations on land and in water within limits that permit life. Also, because organisms are made of primarily water, they are better able to resist changes in their own temperature than if they were made of a liquid with lower specific heat. Okay. So, water's high specific heat. The ability of water to stabilize temperature stems from its relatively high specific heat. Specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. The specific heat of water is 1 calorie per gram and per degree Celsius. Due to the high specific heat of water will change its temperature less than other liquids when it absorbs or loses a given amount of heat. Specific heat can be thought of as a measure of how well a substance resists changing its temperature when it's absorbed or releases heat. Water's high specific heat can be traced to hydrogen bonding. Heat must be absorbed for hydrogen bonds to break. Heat must be released when hydrogen bonds form. The benefit of water's high specific heat. Water serves to moderate air temperatures in coastal areas. It stabilizes ocean temperatures, which is favorable for marine life, and it keeps temperature fluctuations on land and in water within limits that permit life. Evaporative cooling. Molecules of any liquid stay close together because they are attracted to one another. Molecules moving fast enough to overcome these attractions can depart the liquid and enter the air as a gas, vapor. This transformation from a liquid to a gas is called vaporization, or evaporation. Recall that the speed of molecular movement varies, and the temperature is the average kinetic energy of molecules. Even at low temperatures, the speediest molecules can escape into the air. Some evaporation occurs at any temperature. A glass of water at room temperature, for example, will eventually evaporate completely. If a liquid is heated, the average kinetic energy of molecules increases and the liquid evaporates more rapidly. Heat of evaporation is the quantity of heat a liquid must absorb for 1 gram of it to be converted from liquid to the gaseous state. For the same reason that water has a high specific heat, it also has a high heat of vaporization relative to most other liquids. To evaporate 1 gram of water at 25 degrees Celsius, about 580 calories of heat is needed, nearly double the amount needed to vaporize a gram of alcohol or ammonia. Water's high heat of vaporization is another emergent property resulting from the strength of its hydrogen bonds, which must be broken before the molecules can exit from the liquid in the form of water vapor. The high amount of energy required to vaporize water has a wide range of effects. On a global scale, for example, it helps moderate Earth's climate. A considerable amount of solar heat absorbed by tropical seas is consumed during the evaporation of surface water. Then, as moist tropical air circulates poleward, it releases heat as it condenses and forms rain. On an organismal level, water's high heat of vaporization accounts for the severity of steam burns. These burns are caused by the heat energy released during formation of chemical bonds when steam condenses into liquid on the skin. As liquid evaporates, the surface of the liquid that remains behind cools down. Its temperature decreases. This evaporative cooling occurs because the hottest molecules, those with the greatest kinetic energy, are the most likely to leave as gas. It is as if the 100 fastest runners at a college transferred to another school. The average speed of the remaining students would decline. Evaporative cooling of water contributes to the stability of temperature in lakes and ponds and also provides a mechanism that prevents terrestrial organisms from overheating. For example, the evaporation of water from the leaves of plants helps keep the tissues in the leaves from becoming too warm in the sunlight. Evaporation of sweat from human skin dissipates body heat and helps prevent overheating on a hot day or when excess heat is generated by strenuous activity. High humidity on a hot day increases discomfort because the high concentration of water vapor in the air inhibits the evaporation of sweat from the body. Animals without sweat glands, such as elephants, may spray water on themselves to cool down. And look at the little elephant. Okay. So evaporative cooling. I wrote, the transformation from a liquid to a gas is called vaporization or evaporation. If liquid is heated, the average kinetic energy of molecules increases and the liquid evaporates more rapidly. Heat of vaporization is the quantity of heat a liquid must absorb for 1 gram of it to be converted from liquid to gaseous state. For the same reason water has a high specific heat, it also has high heat of vaporization relative to most other liquids. Water's high heat of vaporization results from the strength of its hydrogen bonds, which must be broken before molecules can exit from liquid to gas. The high amounts of energy needed to vaporize water has a wide range of effects. Globally, it moderates Earth's climate. Solar heat absorbed by the seas is consumed during evaporation. The moist air releases heat as it condenses and forms rain. Evaporative cooling. As liquids evaporate, the surface left behind cools down. a result from when molecules with the greatest kinetic energy changes from liquid to gaseous state, contributes to the stability of temperature in lakes and ponds, and prevents terrestrial organisms from overheating. Floating of ice on liquid water. Water is one of the few substances that are less dense as a solid than as a liquid. As a result, ice floats on liquid water. While other materials contract and become denser when they solidify, water expands. The cause of this exotic behavior is, once again, hydrogen bonding. At temperatures above 4 degrees Celsius, water behaves like other liquids, expanding as it warms and contracting as it cools. As the temperature falls from 4 degrees Celsius to 0 degrees Celsius, water begins to freeze because more and more of its molecules are moving too slowly to break hydrogen bonds. At 0 degrees Celsius, the molecules become locked in a crystalline lattice, each water molecule hydrogen bonded to 4 partners. The hydrogen bonds keep the molecules at arm's length, far enough apart to make the ice about 10% less dense, 10% fewer molecules in the same volume than liquid at 4 degrees Celsius. When ice absorbs enough heat for its temperature to rise above 0 degrees Celsius, hydrogen bonds between molecules are disrupted. As the crystal collapses and the ice melts, the molecules have fewer bonds, allowing them to slip closer together. Water reaches its greatest density at 4 degrees Celsius, and then begins to expand as the molecules move faster. Even in liquid water, many of the molecules are connected by hydrogen bonds, though only transiently. The hydrogen bonds are constantly breaking and reforming. The ability of ice to float due to its lower density is an important factor in the suitability of the environment for life. If ice sank, then eventually ponds, lakes, and even oceans would freeze solid, making life as we know it impossible on Earth. During the summer, only the upper few inches of ocean would thaw. Instead, when a deep body of water cools, the ice floats, insulating the liquid water below. This prevents it from freezing and allowing life to exist under the frozen surface, as shown as figure 3.1. Besides insulating the water below, ice also provides a solid habitat for some animals, such as polar bears and seals. Many scientists are worried that these bodies of ice are at risk of disappearing. Global warming, which is caused by carbon dioxide and other greenhouse gases in the atmosphere, is having a profound effect on icy environments around the globe. In the Arctic, the average air temperature has risen 2.2 degrees Celsius since 1961. This temperature increase has affected the seasonal balance between Arctic sea ice and liquid water, causing ice to form later in the year, to melt earlier, and to cover a smaller area. The rate at which glaciers and Arctic sea ice are disappearing is posing an extreme challenge to animals that depend on their ice for survival. Okay. Floating of ice on liquid water. Water is one of the few substances that are less dense as a solid than as a liquid. As a result, ice floats on water. Other materials contract and become denser. Water expands due to hydrogen bonding. From 4 degrees Celsius to 0 degrees Celsius, water molecules are moving too slowly to break bonds. At 0 degrees Celsius, water molecules lock into a crystalline lattice, each water molecule hydrogen bonded to 4 partners. Hydrogen bonds keep molecules at arm's length, making ice 10% less dense with 10% fewer molecules in the same volume. Hydrogen bonds are constantly breaking and reforming. Ability for ice to float on water makes it an important factor in the suitability of the environment for life. It prevents the water below ponds, lakes, and even oceans from freezing completely, thus sustaining life. Ice also provides a solid habitat for animals such as polar bears and seals. Many scientists are worried that bodies of ice are at risk for disappearing. Excuse me. Average air temperature has risen 2.2 degrees Celsius since 1961, affected seasonal balance between Arctic sea ice and liquid water, causing ice to be formed later in the year to melt earlier and to cover a smaller surface area. The rate at which glaciers and Arctic sea ice are disappearing is posing a challenge to animals that depend on ice for survival. Okay. Water, the solvent for life. A sugar cube placed in a glass of water will dissolve. In time, the glass will contain a uniform mixture of sugar and water. The concentration of dissolved sugar will be the same everywhere in the mixture. A liquid that is a completely homogeneous mixture of two or more substances is called a solution. The dissolving agent of a solution is called a solvent. The substance that is dissolved is called the solute. In this case, water is the solvent and sugar is the solute. An aqueous solution is one in which the solute is dissolved in water. Water is the solvent. Water is a very versatile solvent, a quality we can trace to the polarity of the water molecule. Suppose, for example, that a spoonful of table salt, the ionic compound sodium chloride, is placed in water. At the surface of each crystal grain of salt, the sodium and chloride ions are exposed to the solvent. These ions and regions of the water molecules are attracted to each other due to their opposite charges. The oxygen of the water molecules have regions of partial negative charge that are attracted to sodium cations. The hydrogen regions are partially positively charged and are attracted to the chloride anions. As a result, water molecules surround the individual sodium and chloride ions, separating and shielding them from one another. The sphere of water molecules around each dissolved ion is called a hydration shell. Working inward from the surface of each salt crystal, water eventually dissolves at all the ions. The result is a solution of two solutes. Sodium cations and chloride anions mix homogeneously with water, the solvent. Other ionic compounds also dissolve in water. Seawater, for example, contains a great variety of dissolved ions, as do living cells. A compound does not need to be ionic to dissolve in water. Many compounds made up of non-ionic polar molecules, such as sugar and the sugar cube mentioned earlier, are also water-soluble. Such compounds dissolve when water molecules surround each of the solute molecules, forming hydrogen bonds with them. Even molecules as large as proteins can dissolve in water if they have ionic or polar regions on their surface. Many different kinds of polar compounds are dissolved, along with ions, in the water of such biological fluids as blood, the sap of plants, and the liquid within all cells. Water is the solvent of life. So for water, the solvent of life, I wrote, a solution is a homogeneous mixture of two or more substances. Solvent, the dissolving agent of a solution. Solute, the substance that is dissolved. Aqueous solution is where any solute is dissolved in water. Water is a very versatile solvent due to the polarity of the water molecule. Oxygen's partial negative charge attracts cations. Hydrogen's partial positive charge attracts anions. Water molecules surround the individual ions, separating and shielding them from one another. Hydrogen shell Hydration shell is a sphere of water molecules around each dissolved ion. Works inward from the surface of the salt crystal. Water eventually dissolves all the ions. A compound does not need to be ionic to dissolve in water. Many compounds are water soluble. Okay. So, hydrophilic and hydrophobic substances. Any substance that has an affinity for water is said to be hydrophilic. From the Greek hydro, water, and philos, water, loving. Philos, loving. In some cases, substances can be hydrophilic without actually dissolving. For example, some molecules in cells are so large that they do not dissolve. Another example of a hydrophilic substance that does not dissolve is cotton, a plant product. Cotton consists of giant molecules of cellulose, a compound with numerous regions of partial positive and partial negative charges that can form hydrogen bonds with water. Water adheres to the cellulose fibers. Thus, a cotton towel does a great job of drying the body, yet it does not dissolve in the washing machine. Cellulose is also present in the walls of water-conducting cells in a plant. You read earlier how the adhesion of water to these hydrophilic walls helps water move up the plant against gravity. There are, of course, substances that do not have affinity for water. Substances that are non-ionic and non-polar, or otherwise cannot form hydrogen bonds, actually seem to repel water. These substances are said to be hydrophobic, phobos meaning fearing. An example from the kitchen is vegetable oil, which, as you know, does not mix stably with water-based substances such as vinegar. The hydrophobic behavior of oil molecules results from a high number of relatively non-polar covalent bonds, in this case bonds between carbon and hydrogen, which share electrons almost equally. Hydrophobic molecules related to oils are major ingredients of cell membranes. So hydrophilic and hydrophobic substances, I wrote hydrophilic, water-loving, any substance that has affinity for water. Some substances can be hydrophilic without actually dissolving, such as cotton, made out of cellulose, which is a compound with numerous regions of partial positive and negative charge that can form hydrogen bonds with water. Hydrophobic is water-fearing, substances that are non-ionic and non-polar or cannot form hydrogen bonds that seem to repel water. Vegetable water versus water-based substances results from a high number of relatively polar covalent bonds, relatively non-polar covalent bonds which share electrons almost equally. Hydrophobic molecules are major ingredients of cell membranes. Okay. Solute concentration in aqueous solutions. Most of the chemical reactions in organisms involve solutes dissolved in water. To understand such reactions, we must know how many atoms and molecules are involved and calculate the concentration of solutes in the aqueous solution. When carrying out experiments, we use mass to calculate the number of molecules. We must first calculate the molecular mass, which is the sum of all the masses of all the atoms in the molecule. As an example, let's calculate the molecular mass of table sugar, sucrose, C12H22O11, by multiplying the number of atoms by the atomic mass of each element. See the periodic table at the back of the book. In round numbers of Daltons, the mass of a carbon atom is 12, the mass of a hydrogen atom is 1, and the mass of a oxygen atom is 16. Thus, sucrose has a molecular mass of 342 Daltons. So when you multiply the mass and the number of atoms, which is listed in the element name, you get 342 Daltons. Because we can't weigh out small numbers of molecules, we usually measure substances in units called moles. Just as a dozen always means 12, a mole represents an exact number of objects, which is 6.02 times 10 to the 23rd, which is Avogadro's number. Because of the way in which Avogadro's number and the unit Dalton were originally defined, there are 6.02 and 10 to the 23rd Daltons in 1 gram. Once we determine the molecular mass of a molecule such as sucrose, we can use the exact number 342 but with the unit gram to represent the mass of 6.02 times 10 to the 23rd molecules of sucrose, or 1 mole of sucrose, sometimes called the molar mass. Basically, to obtain 1 mole of sucrose in the lab, therefore, we weigh out 342 grams. So that was a little confusing, but once we go over the notes, it'll be a lot easier. The practical advantage of measuring a quantity of chemicals in moles is that 1 mole of a substance has exactly the same amount of molecules as a mole of any other substance. If the molecular mass of substance A is 342 Daltons, and that of substance B is 10 Daltons, then 342 grams of A will have the same number of molecules as 10 grams of B. A mole of ethyl alcohol also contains 6.02 times 10 to the 23rd molecules, but its mass is only 46 grams. Because of the mass of the molecule of ethyl alcohol is less than that of a molecule of sucrose. Measuring in moles makes it convenient for scientists working in the laboratory to combine substances in fixed ratios of molecules. How would we make a liter of solution consisting of 1 mole of sucrose dissolved in water? We would measure out 342 grams of sucrose and then gradually add water while stirring until the water was completely dissolved. We would then add enough water to bring the total volume of the solution up to 1 liter. At that point, we would have 1 molar solution of sucrose. Molarity, the number of moles of solute per liter of solution, is the unit of concentration most often used by biologists for aqueous solutions. The water's capacity as a versatile solvent complements the other properties discussed in this chapter. Since these remarkable properties allow water to support life on Earth so well, scientists who seek life elsewhere in the universe look for water as a sign that a planet might sustain life. Okay. So here I wrote solute concentration in aqueous solutions. Most chemical reactions in organisms involve solutes dissolved in water. We need to know how many atoms and molecules are involved and calculate the concentration of solutes in the aqueous solution, the number of solute molecules in a volume of solution. First, calculate the molecular mass, which is the sum of the masses of all atoms in a molecule. So, taking sucrose, we have C12H22 and O11. Carbon mass is 12, hydrogen mass is 1, oxygen mass is 16. You multiply the number of the atoms available to the mass of the atom, and then you add them together as you would, and you get 342 Daltons. So I hope that makes sense to you guys, and it's not too confusing. You just have to practice a little bit with this one, I think. Okay? A mole represents the exact number 6.02 times 10 to the 23rd, Avogadro's number. There is 6.02 and times 10 to the 23rd Daltons in grams. We use the same number 342 with the unit gram to represent 6.02 times 10 to the 23rd molecules of sucrose, 1 mole of sucrose. So 1 mole of sucrose is 342 grams. A mole of one substance has exactly the same number of molecules as a mole of any other substance. And molarity. The number of moles of solute per liter of solution is a unit of concentration. Okay. Possible evolution on life on other planets. Evolution. Biologists who look for life elsewhere in the universe, also known as astrobiologists, have concentrated their research on planets that might have water. More than 800 planets that have been found outside our solar system, with evidence for the presence of water vapor on a few. In our own solar system, Mars has been a focus of study. Like Earth, Mars has an ice cap on both poles. Images from spacecraft sent to Mars showed that ice is present just under the surface of Mars, that enough water vapor exists in its atmosphere for frost to form. In 2015, scientists found evidence of water flowing on Mars, and a study using radar in 2018 concluded that there is a large reservoir of liquid water 1 mile below the surface ice. Drilling below the surface may be the next step in the search for signs of life on Mars. And if any life forms or fossils are found, their study will shed light on the process of evolution from an entirely new perspective. Okay. So possible evolution of life on other planets. Astrobiologists are biologists who look for life elsewhere in the universe and concentrates on whether a planet has water. Mars is our focus of study, has 2 ice caps at both poles, evidence of flowing water on Mars and a reservoir of water 1 mile under ice, and looking for evidence of life forms or fossils. Okay, so that is it for this concept 3.2. Next chapter we'll be going over concept 3.3. Acidic and basic conditions affect living organisms. Okay, so I wish you guys luck on your studies. I hope that my videos have been helping. I hope that my notes are sufficient and that they make it easier for you to understand. And yeah, so best wishes. See you guys next time. Bye.